At this very moment, somewhere in the world, warehouse construction blueprints are being redrawn. The reason is singular. The movement paths that robots require do not align with conventional design assumptions. The era of humans designing spaces purely for humans is already over. AI is now simulating millions of robot movement trajectories, and those results are dictating where structural columns are placed, how high ceilings must rise, and even redefining the fundamental shape of buildings themselves. This video is not a simple technology overview. It addresses the very real paradigm shift in design thinking that architects and planners need to understand right now, before the next project lands on your desk. Traditional warehouse design always began from human movement as its foundational baseline. Aisle widths were set at 2.5 to 3 meters, calibrated around forklift turning radii. Ceiling heights hovered around 6 meters, governed by worker safety regulations. Then AMRs, autonomous mobile robots, arrived on warehouse floors. And those long-established benchmarks began to crumble entirely. Robots operate under fundamentally different physical constraints than humans. Their turning radius approaches zero. Their vertical movement speed is perfectly consistent. They repeat the same movement patterns 24 hours a day, without fatigue or deviation. The critical problem emerges when hundreds of these robots operate simultaneously. Conventional layout designs create bottlenecks, collision avoidance algorithms become overloaded, and operational efficiency drops sharply. This is precisely where AI path optimization engines enter the picture. Through millions of simulations, they reverse engineer the spatial configurations that minimize robot traffic congestion and convert those findings directly into architectural design data that reshapes buildings before construction begins. In practice, AI path optimization reshapes 5 specific architectural elements. First, column spacing. The traditional 12-meter structural grid is being recalibrated to 10.8 or 14.4 meters to align with robot movement grids, because column positions that conflict with robot travel patterns create dead zones that erode operational efficiency. Second, ceiling height. The introduction of vertical conveyor robots is pushing minimum clear heights to 14 meters. And in high-density facilities globally, designs exceeding 30 meters are now emerging. Third, floor flatness and load capacity. AMR charging dock concentration zones carry point loads more than 3 times higher than general floor areas, making structural reinforcement a non-negotiable consideration from the earliest design stage. Fourth, lighting and electrical infrastructure. Robots do not need natural daylight, but uniform. Controlled illumination is technically essential to prevent vision sensor malfunctions, making lighting a functional engineering requirement rather than an aesthetic preference. Fifth, entrance and dock placement. AI analyzes inbound and outbound cargo flows independently and recommends dock configurations that minimize peak-hour truck queuing, a level of operational intelligence now flowing directly into the architect's design brief. So what tools should architects and designers be using right now? Here is the validated, step-by-step, AI-based logistics design workflow that leading global firms are applying in practice. Step 1. Operational data collection. Gather your client's SKU count, daily order volume, and peak hour traffic patterns. This is the input that powers every simulation that follows, and without it, AI optimization has nothing to work with. Step 2. AI path simulation. Use layout optimization engines from established automation vendors such as AutoStore, 6 River Systems, or Symbotic, or deploy independent simulation platforms like Analogic or FlexSim to run robot traffic scenarios across millions of iterations. Step 3. BIM, reverse design. Feed the simulation output back into Revit or ArchiCAD to recalibrate column grids, slab specifications, and structural openings. BIM integrated AI review systems are now reported to detect approximately 78% of design errors at the initial review stage alone, making early simulation investment highly defensible. At this stage, AI-assisted design review has also been shown to reduce overall review time by approximately 40%. Step 4. Digital twin validation. Before design sign-off, replay real operational scenarios inside a digital twin environment to identify and eliminate bottleneck zones before a single foundation is poured. This 4-stage iterative cycle is now the recognized standard workflow among the world's leading logistics architecture firms. Here is where an honest conversation about market reality is needed. The global showcase projects are impressive, but the majority of logistics facility projects worldwide, particularly across rapidly developing markets in Southeast Asia, Eastern Europe, Latin America, and beyond, still rely on 2D CAD drawings and experience-based design judgment. The reasons are layered and familiar. A. Simulation tool licensing costs remain a genuine barrier for small and mid-sized design firms. Structured data sharing between facility operators and architects is inconsistently practiced across markets, and in many development contexts, construction commitments must be locked in before automation procurement decisions are even made, meaning robot readiness is never integrated at the design stage. The result is predictable and costly. Within 1 to 2 years of opening, facilities begin expensive retrofits, raising ceilings, repositioning columns, rerouting electrical infrastructure to accommodate the robots that eventually arrive. These post-occupancy modifications routinely run into millions of dollars per facility, representing entirely avoidable waste. For architects working within this reality, 2 immediate responses are practical. First, adopt flexible structural modules that treat robot integration as a future possibility by default, even when clients say automation is not on their roadmap. Second, proactively present clients with the data that makes AI simulation investment a defensible business case before project scope is locked. Let us look a little further ahead. As AI path optimization technology matures toward 2030, how will the role of the logistics architect fundamentally change? The scenario that industry experts consistently point to is becoming sharply defined. Architects will no longer be the professionals who determine spatial dimensions. I will calculate optimal dimensions. Instead, architects will own the territory that AI systems cannot enter. The judgment calls that balanced structural safety against operational efficiency, the interpretation of building codes, regulatory frameworks, and permitting contexts across diverse jurisdictions, and the design of safe, dignified working environments for the human workers, who will always share these facilities with machines, regardless of how advanced automation becomes. What is striking is that the more sophisticated an AI design system becomes, the more it actually demands meaningful human architect involvement in final decisions. That is because AI optimizes numbers, but it cannot comprehend the full human context of lived experience within a space, nor the social and ethical weight of the choices being made. Ultimately, AI and architects are not competitors. The structure taking shape is a collaboration. AI computes the space, and architects make that space meaningful. The firms that understand this distinction earliest will define what world-class logistics architecture looks like in 2030 and beyond. As we have seen today, AI and robot path optimization are fundamentally restructuring the entire lifecycle of logistics facility design. A single column position, a difference of a few meters in ceiling height. These decisions now carry operational efficiency consequences worth millions. And increasingly, it is AI that makes the first proposal, while the architect makes the final call. Which brings us to a question worth sitting with. On your next logistics facility project, when a client tells you they have no plans to introduce robotics, what design decisions will you make? If adopting a full AI simulation platform is not immediately feasible for your firm or your project budget, the most practical and defensible choice for both you and your client is to design to a robot-ready structural module as your default baseline. It costs little at the design stage, and it protects against the far greater cost of retrofitting later. Share your thoughts in the comments below. How are you approaching robot readiness in your current projects? In the next video, We will bring real cost comparison data between AI-designed